Okay, we can go ahead and get started, and people will filter in as I'm talking. So, hope everyone had a nice lunch. I have a few announcements before we get started with the afternoon session. First, Kong would like you to know that the survey now should work, or it should have the appropriate questions, so you can go ahead and fill that out to give him some feedback from his talk. Second, before the juniors party tonight at 6:30, we'll have some time. So if you'd like, I think some people will be providing tours of STAR. So if you want to do that, if you haven't seen it yet, for example, that could be a good opportunity to go take a look. Yeah.
Bill will go with them.
Yeah, Bill will also, I think, go with people.
And it sounds like, something like 5:15, something like this?
Yeah, that sounds good. So maybe we can all meet around here in the, just outside the room at that time. Okay, so without further ado, we have a real treat for you all for this afternoon session. Two very pivotal figures in STAR. We have a bit later the founding spokesperson and one of the first council chairs will both tell you a bit about some very important things. So Bill will start with how RHIC delivers STAR, its beam that it uses for physics. So Bill, take it away.
All right, thank you. One other thing that I was probably the first at was first junior member in STAR. Back when, writing the letter of intent, and then the collaboration was formed, and actually helped write all the bylaws and such, writing in the junior members. So the topic I got is up here on the top. How does RHIC get beams ready for our use? I should have seen Kong's talk, and I don't have Drupal access to see the slides, but I'm probably going to violate a lot of things. I greatly acknowledge the help I got from Travis Shrey, Elke Aschenauer, Chiu Lu Luau, Haixing Huang, and Michiko Mini for slides and discussion related to this talk. Here's the complex here. RHIC is actually a series of a bunch of injector accelerators, and I'm going to walk through them one by one. You can see the RHIC ring and STAR at 6 o'clock. The beams come in from here, and they actually get injected into RHIC on both sides of STAR. So starting with the injector chain, RHIC again is up here at the top. Nothing goes into RHIC that doesn't come out of the AGS. Nothing comes out of the AGS that doesn't come out of the booster. So this part is inviolate. But then there are three sources of beam: the LINAC, the electron beam ion source, and the tandem Van de Graaff. The LINAC is shown here. It's a long linear accelerator, but this building is over 400 feet long, a long straight line with a hallway, if you will. The tandem Van de Graaff over here, if you were to walk across the street on this side of the physics building, that's where it resides. And then it's got a long transfer line to get it over to the booster. And then the EBIS source, electron beam ion source, sits right about here. It's in the LINAC building. But again, these are the three sources for beams. Starting with the LINAC, it came online in 1971 as an addition to the alternating gradient synchrotron, which we'll hear about. Two sources of protons, a high-intensity source that they used for the Brookhaven Life Sciences isotope production program, mostly medical isotopes, and then the polarized proton source OPUS, which I think stands for optically pumped polarized ion source. The beam then gets transported into the booster. For the protons, it accelerates is actually H-, not protons, up to 200 MeV. The average current can get up to 135 microamps, and then it's transferred into the booster. As it goes into the booster, they strip off the electrons, and it becomes a proton beam. And this is a picture inside of the LINAC itself. The EBIS source. This is the source for all ion beams for the heavy ion running. It lives right about here in this building, although again, it doesn't go through LINAC. It's got its own transfer line to get it into the booster. The final acceleration between the EBIS and the booster is a fixed frequency small LINAC. So all beams go into the booster at the same velocity, which means the same RF frequency. EBIS is able to switch beams very rapidly. On the order of seconds. They could go from gold to carbon to something else, and indeed they use that when they do the galactic cosmic ray program at the NSRL, the NASA Space Lab. The tandem Van de Graaff, this has been retired as an injector for RHIC, but we still use it now and then. If the EBIS source goes down or something, here's a picture of one of the 2 large tanks. Again, it sits across the street behind me here. There's a large transfer line, and then it goes into the booster. The beams are they're stripped to whatever state they'd like them in the transfer line as they go over there. Moving on, we get to the booster then. This was completed in 1991, sort of in preparation for the RHIC program. And indeed, there was a heavy iron program that was run in the 90s here that a lot of people that are still involved in RHIC took part in, and the booster helped that. It's a 200-meter circumference synchrotron. The ion beams enter in the MeV range, and they exit in the hundreds of MeV per nucleon for the ions. For the proton beams, they go in at about 200 MeV, they come out at about 2.5 GeV. In the booster, they can do bunch merging, which can increase the intensity of the bunch. So you could put in, say, 4 or 6 bunches in separate RF buckets into the booster, and then by reducing the voltage on those cavities, those radio frequency cavities, and increasing the voltage on ones that have a lower frequency, they can push the bunches together and get more intensity per bunch before they inject it into the AGS and then finally into RHIC. The cycle time is pretty quick, about 100 to 250 milliseconds. This is from injection to extraction. And you can have multiple cycles to fill up the AGS ring, depending on how you're operating. Moving on, the alternating gradient synchrotron. This has been one of the world's premier accelerators, really, for about 60 years now. Very intense proton source, 800 meters in circumference. The name is derived from the concept, which was new at the time, novel for this accelerator, alternating gradient focusing. The magnets that go around the ring alternate focusing in and focusing out. And what that does is it allows them to focus the beam simultaneously in the vertical direction and the horizontal direction as they accelerate and store the beams. The ions enter at about 100 MeV range as they come out of the booster, or about 37% of the speed of light, and they exit about 10 GeV for injection into RHIC, close to the speed of light. And we'll get back to that later on, what actually happens in the RHIC synchrotron. Most ions are fully stripped. Gold isn't quite stripped. It's got 2 electrons on it, and the final 2 electrons are taken off in the transfer line over to RHIC. Protons go into the AGS at 2.5 GeV. They exit at about 25. The approximate sign is, when it comes to polarized proton running, like we're going to do this year, everything matters. Absolutely everything matters. And one of the things they found is by lowering this number a tiny bit, they can get a little bit more polarization out of the AGS. So I think they actually injected about 23.8. And we'll see where they end up this year, because they are making some changes to the AGS for spin running. The cycle lengths, 4 seconds for protons. This is, again, the time between injection and extraction. For gold or ions, it's 6.8 seconds. This plays directly into how long it takes to load up the RHIC rings before they can accelerate them in energy. And they load 222 bunches in RHIC for each fill, for a full load anyway. And if you take the 4 seconds times 222, you'll find it takes about 15 minutes to load up RHIC. Yeah, 1 bunch per acceleration cycle for protons. And for ions, you can have more than 1, so this number gets knocked down to loading time. And that's a picture inside the AGS. This brings us to RHIC itself, 3,800 meter circumference cyclotrons. There's 2 of them, 1 in each direction. In each direction here, another schematic of RHIC. Stars at 6 o'clock, and as we mentioned earlier, the beams come in and they get injected going in both directions. If you're looking from the top at RHIC, the yellow beam goes counterclockwise, the blue beam goes clockwise. So again, the ion beams come in at about 10 GeV, and they're stored at whatever energy you want to run at, typically 100 GeV. This is a slide I got from the accelerator people. I should have modified this, because this is what RHIC was designed for. For the STAR low energy program, of course, we ran at energies much lower than that, down to about 3.65, I think, GeV per nucleon. That was actually operating below the design spec for the accelerator, where magnets aren't so well behaved and mapped. But indeed, they could do it, and in that case, you were injecting it at that energy, whatever energy you're going to run at. Say 3.5 GeV is the lowest. Protons enter at about 25 GeV, and they can be stored at up to 255 GeV. This year, my understanding is we're going to start the run with 100 GeV polarized, transversely polarized protons. This is the only polarized proton collider in the world. Store lengths vary. If you've been on shift, you know sometimes for the low energy it might be 15 minutes for the lowest energies. If you've got protons in there and there's a problem with the injector chain, we've kept the beam for a whole day, and it just keeps going around. 111 bunches are filled, 9 are left empty for the abort gaps, so there's a 120 bunch pattern when RHIC is up and running. Typical bunch intensities are about 1 billion ions per bunch. I got this from one of the collider colleagues, you know, where they say typical is probably closer to max, but 1 billion per bunch for the protons, 100 billion per bunch for the proton, or for the ions, 100 billion for the protons. So the RHIC complex, come back to it. Here's a picture of it here. The injection sources, the LINAC, the booster, the AGS, and RHIC. What we're going to go on now to talk about a bit is how you get polarized protons and how you keep them polarized to take this data. And you can see there are a lot of polarimeters called out here. So spin depolarizing resonances. In a perfect accelerator, the spin of the proton just precesses around the dipole field that bends the particle into the circle of the synchrotron. The spin tune, which you'll hear talked about during the run, QS, this is the number of times the spin goes around the dipole vector for each revolution around the RHIC ring. And it's given by this G factor times gamma, Lorentz factor. They have things called imperfection resonances, and if there's a dipole error or there's a quadrupole that's misaligned or something, what it'll do is it'll kick this. This wants to stay aligned with the dipole field, either up or down, but if there's imperfection somewhere, it'll get a kick, and it'll try to depolarize the beam. The locations are given by any time this factor is equal to an integer. And then there are intrinsic resonances, and this is horizontal focusing fields from the betatron oscillation. When a beam goes around a synchrotron, you can think of it as a circle. A perfect circle would be an idealized life, but it actually oscillates. You can think of it like a standing wave going around in a circle, coming into the orbit, out of the orbit. It does it both horizontally and vertically. It's the vertical betatron oscillations that give you this horizontal focusing that try to depolarize the beams. Moving on. So the challenge is, how do you keep this thing polarized as you're going around with these two sources of resonances? Here's a picture of a polarized spin vector, if you will, processing around the dipole field, and now it's getting some kick, some horizontal kick, a magnet in the wrong place or something, or again, it's gone vertically high into a quadrupole. After one full betatron oscillation, if things are aligned, it's going to come around to that same point and it's going to get kicked again. So whatever this was to depolarize it, it's going to do it again, it's going to do it again, and before you know it, you're depolarized. Keep in mind, a beam in RHIC goes around the circumference of RHIC about 78,000 times per second. So if there's something that's trying to knock this offline, it's going to hit it frequently. To give you an idea how many depolarizing resonances there are in RHIC, this is just a chart of them, and the point here is that there are a lot. And typically the higher the energy, the higher the depolarizing effect. There's a innovative accelerator concept that was developed back in the 1970s by two Russian gentlemen, and it's an alternating series of vertical and horizontal dipole magnets. What the effect is you take the spin vector and it rotates it around 180 degrees relative to a horizontal axis, and this is a kind of a conceptual drawing of that. The beam trajectory actually gets bounced around a bit while it goes through this motion. You know, here it's a matter of how big this rotation is versus whatever depolarizing kicks it gets. The much easier way to think about it is that when you're operating with Siberian snakes, the spin tune is a half integer and it's energy independent. We talked earlier that a spin tune of 1 means that the spin precesses around the dipole direction once per revolution. So if you've got a spin tune of 1, every time you come to the same part of the ring, you're going to get whatever imperfection resonance hits you again. If it's a half, and actually the next slide is an easier way to present this. If it's a half integer, what it means is that, pardon me, wrong button. Here's the dipole field, here's the spin vector, here's the precession around here. The first time coming around, this gets knocked this way. With a spin tune of a half, it means the next time it comes around, the spin vector's on the other side, and it's going to kick it back. So the end result is it maintains the polarization. To me, you know, just a miracle that these beams, they go around 78,000 times a second. Let me see the next plot. This doesn't quite do it. But each time around in RHIC, and we'll see a plot of it in a minute, there are 2 snakes in each ring. So that polarization vector, every time it goes through the snake in RHIC, it flips direction. So twice every time around, going around at 78 kilohertz, so about 156 kilohertz, that spin is going up and down. If we were running with spin rotators, you'd add on another 4 times per revolution. It's just amazing that you're flipping around that much, and yet we can maintain polarization for 8 hours in the collider. So some main figures of merit for polarized proton running. One is the luminosity, there's a formula for it here. And then the other one is the beam polarization, which is kind of a statistical average of how many of the spin vectors are pointing in the direction you want them to, whether it's up or down. This must be the PDF. If it was the PowerPoint, I noticed when I was running this this morning, these are slides I got from Elka, and Elka always has nice transitions. So they were rotating cubes. But this is an example of what it means for beam polarization. It's a very simple example, spin 1/2 particles where they can either be spin up or spin down. The polarization is the number in the direction you want. In this case, spin up versus number in spin down over the sum of the two. If you've got 4 particles and they're all in the same, have their spin vectors in the same direction, you run through this formula, you get 100% polarized. Flip one of them, you run through the formula, you're down to 50%. Flip 2 of them, you're down to 0 polarization. So when you're hearing the polarization numbers, and there'll be something hopefully above 50, typically when we're running, you can kind of keep this simple picture in mind, what it means. So how do we measure the polarimetry? There are 3 main ways in RHIC. Some of these polarimeters get replicated in various places. One is the hydrogen gas jet polarimeter. It's a very dilute hydrogen atomic jet that the proton beam in RHIC passes through. Its key feature is this gives you the absolute polarization of the beam. And the H-jet polarimeter is it normalizes all the other polarimeters. It allows you to determine what their analyzing powers are, and then you can take their measured asymmetries and turn it into a polarization. So that's the key. It gives you the absolute polarization. It's very slow, so you have to integrate a long time, many stores. P-carbon polarimeter is very fast, so you can scan the polarization of the beam often. It takes about 1/2 minute. And it also gives you both the lifetime of the beam, because you can do it every hour or every 2 hours during the fill, and it'll give you the polarization profile. And I'll show a picture of that. It's actually more polarized at the center of this Gaussian beam distribution than at the tails. But again, it needs to be normalized to the hydrogen jet. And then local polarimeters that, again, I got this, I see Elke in the back. I got this from her from an older talk. I should have put an S in here because it's S Phoenix now. And star, and it defines the spin direction in experimental areas. So all of these systems are necessary. Here is a look at the RHIC ring again. This is a picture of the hydrogen jet. We're going to see another one of those. Here's the P-carbon apparatus over here. This is a ZDC. S Phoenix started using a forward neutron asymmetry to measure their local polarimetry. And stars started using the intertiles of the BBC beam counter to measure polarization. So the hydrogen jet, 12 o'clock, the p-carbon polarimeter is close by. You'll see there's a polarimeter at the end of the LINAC that really measures what's coming out of the source, and then there are polarimeters in the AGS. So how to measure beam polarization? You get some process where for a transversely polarized proton beam scattering off of another proton, it'll have a left-right scattering asymmetry. You measure how many go to the left versus how many go to the right. This is your physical asymmetry, the number left minus the number left, right over the sum of the two, and it gives you the analyzing power times the polarization. So the analyzing power is just this multiplicative factor between the measured asymmetry and the polarization of the beam. Flipping the equation around a little bit, polarization is the measured asymmetry dividing by this analyzing power. This is a picture of the hydrogen gas jet. It's a large apparatus. You see it's almost 4 meters tall. The jet direction is down. The beam comes through like this. It can move transverse to the beam, so they can put the RHIC beam in the center of the device, depending on what the orbit of the beam is in any given year through this part of the collider. And you can get a statistical error on your polarization of about 10% over 1 RHIC store. To get better precision, you want to get as high as you can, you integrate over many stores. And that was this earlier comment. It's a fairly slow device. But again, this gives you the absolute polarization, how is demonstrated on this slide. AN is the analyzing power, the asymmetry of the target over the target polarization. They're both proton beams, so it's also the asymmetry of the beam over the polarization of the beam. Given this fact, you can cancel out the analyzing power, and polarization of the beam is the target polarization divided by the ratio of these asymmetries. The target polarization is measured by the gas jet device with this type of polarimeter. It's about 92% and it's stable. So measuring these two asymmetries and this target polarization, you get the absolute polarization of the beam. And then you use this polarization in the beam to figure out the analyzing power for your other polarimeters. Going on to the p-carbon polarimeter, this is a left-right asymmetry, polarized beam impinging on a carbon atom. The carbon atoms are actually in very thin ribbons. The ribbons are literally just multiple atomic layers thick. I think it's difficult to impossible to actually see them if you have one in front of you. When you start a RHIC run, they'll have carousels full of these ribbons because they burn out eventually from the beam passing through them. And then they'll just change to the next ribbon. Again, the polarization is given by the measured asymmetry divided by the analyzing power. It's a left-right asymmetry. So this is what you're measuring. Here's the beam, here's the carbon ribbon. And what you do is you scan the ribbon through the beam. It's very quick. It takes about 20 seconds, 20 to 30 seconds. It gets you a very high statistical precision because the count rate is high. And it can give you both the polarization profile, vertical and horizontal. And the fact you do this every hour or so, you'll get an idea what the lifetime of the polarization is. It doesn't give you the absolute polarization, but just looking at the asymmetry, you can see how you're losing the polarization. This is a plot showing that. Here you see, here's the proton beam, here's the hydrogen jet target. The jet is much bigger than the beam, so it's not going to give you what the profile is. But you're going to have to correct for this profile, and this gives you an idea how. As you scan the ribbon through the beam, this is an intensity profile of the RHIC beam in arbitrary units. How many particles at a certain distance from the center. This is the polarization profile, and you can see it's far from flat. It's changing by about a factor of 2 when you go from the center to the edges. This is an issue because you have to account for it. At star, a proton hits a proton. What's its polarization? If it's at the center, it's pretty high. If it's at the edge, it's pretty low. So you correct for this when you do the analysis. And the spin group in star are the experts in all of this. So going back to the need for polarimeters, again, we've talked about the H-jet, the p-carbon calorimeters, there's p-carbon in the AGS. And now the local polarimeters at Star and Phoenix, if we're running, in particular for running longitudinal polarization, because the spin rotators try to take that vertical polarization and make it horizontal, either in the direction of the beam or opposite the direction. But if it isn't done perfectly, it can be pointing at any angle. And you've got to figure that out and ideally work with the collider accelerator or the accelerator operators and get that polarization vector as close to in the direction or away from the direction of the beam as you can. And typically, as I recall, if you get it within about 8 or 10 degrees, you've got a very well tuned machine. But you have to check it. Local polarimetry, this is kind of historical. I think Elke made this slide about 9 years ago. Phoenix started early on by looking at asymmetries in forward-going neutrons. And at high XF, what was found is there's a left-right asymmetry with a polarized beam. It wasn't really known that this was going to exist at RHIC energies, but the fact that it did, they use it for a local polarimeter. Star used the beam counter looking at the forward hadrons in the intertiles of the BBC, and there's a left-right asymmetry there. And this was what started with this local polarimeter. When we inject RHIC for polarized running, successive bunches are either spin up or spin down, and then you'll get 2 up, 2 down. They usually run 6 or 12 different spin patterns that they cycle through during the run as a way to limit any systematics associated with the actual spin pattern. And you can see that here, some are up, some are down. Of course, nowadays, Star, when we run this, will not only use the intertiles of the BBC, they use the VPD, and they use the ZDC, and they play them off one another to try to minimize systematics in the local polarimeter measurement. So some typical polarimeter numbers. LINAC polarization is usually in the 80 to 84% range. It's really the opus polarization coming out of the LINAC. The booster polarization more or less retains that. In the booster, there are no intrinsic resonance, some imperfection resonances, and they compensate for that with orbit manipulations. In the AGS, the polarization 67 to 70%. I got this slide from some collider people. This might be on the high end of when things are really going well. There are 2 partial snakes in RHIC. The way that works is every time G gamma hits an integer, it flips the spin. It's going to hit an integer, I would say 40 times, but I asked the accelerator physicist and checked. The spin flips direction 41 times during the AGS acceleration. And then they have partial intrinsic resonances that they compensate with tune jumps. New for this year, they're putting in things called skew quad, a skew quad system. I think there's 15 of these things. And it's going to replace this tune jump. And the expectation is that they'll gain several absolute percent in the polarization, which is huge. If they can go up by 2 or 3% for a spin measurement, this is a huge impact. So in RHIC, the polarization is typically around 55 to 60%. And again, these are pretty good numbers. 2 full snakes per run, per ring. So again, the spin flips twice per revolution. So it's revolving at about 78 kilohertz. So the spin is flipping about 156 kilohertz. It gives the G gamma range here, but it doesn't matter. In RHIC, from the time you inject all the way through the store, it flips the spin twice per orbit. And at this 156 kilohertz rate. This gives you how many resonances there are. Here's a day in the life of RHIC. A lot of you are probably used to this. This is showing ZDC coincidence rates. This is an old slide as well that I got from Elke. I think this is actually Andy. The red and the blue are Phoenix and Star. And this is the length of a store. You dump, you inject, you have another store, you have another store. This is the intensity of the beams in RHIC. This is the beam in the AGS. Here's a link down here. If you look at it during the run, it'll take you all the way down to the EBIS or the LINAC, and you'll see all stages of the acceleration, what they're doing during the day. This is another slide I got from Elke nicely. Many of you are used to this. If you sat on shifts, this is a display that you'll see on the shift leader terminal. They usually put in what they call a pilot bunch just to check that the orbits are right, the tune looks right, and then they'll load up the ring. You can see there's actually two lines here. One line is for the beam that's in the RF bucket that they meant to put it in, and one is for the beam that's the total beam, that's bucketed and that isn't in the bucket. This is very cleanly done. They're both on top of each other. Then they load up the yellow ring. Here's the line where they start acceleration. The red lines are what they call milestones, where they can check the operation of the machine, tweak the tune, or orbit if they have to. Just before they get to flat top, they'll adjust the optics, what they call the beta star. Crudely, I always think of it as a focal length for the experiments. And then that finishes the acceleration ramp. And then there's the collision setup. They'll call it a storage ramp. And they'll do things like cogging, rebucketing, collimation, and steering. They flip physics on, and you should all be aware of that because you know how closely we track your efficiency getting star going after physics on is declared, and then here you are taking the physics program. Here's a picture of the DAC monitor, and just the point I want to make is you may not notice so much, but you can get very good real-time data on whatever it is that RHIC is doing. This is Paige and Tonko does, and it's real time. If they put in a single bunch, you'll see it show up here. As they start loading, you'll see the number of ions go up. You'll see the energy of the RHIC rings. As they do the energy ramp, you'll see it go up. And then this is our clock frequency that we run the experiment on. At full store, it's about 9.38 megahertz, and that's equal to the frequency that the beam's filled bunches come through star. 9.38 million times per second, a filled bunch on a filled bunch. If you think for the ion beams, and you've got 1 billion gold ions in each bunch and a crossing at just over 9 million times a second, and then you think of the rate we take data, 10 kilohertz, 20 kilohertz, what have you, most of the time these beams pass through each other and nothing happens. Of course, STAR is designed to look at every one of those crossings with our trigger counters and see if anything happens, and then you've got all your scalars and such. So this is a very good, useful tool. One thing that amazed me, I'm kind of used to it now, but it drives home what the effect of relativity is. The beam went in at 10 JeV and it goes up to 100 JeV. You might think, boy, they really sped it up. You know, it must be going around the ring faster. This frequency changes by less than 1% between injection and top energy. So you're really not speeding up the beam. You're just adding energy to the beam. It gets heavier, it gets more rigid, and that's why they have to ramp up the magnets to keep the beam going around in a circle before you collide it. So what happens after the collision in this collision setup phase? Typically, you'll see the two ramps, the energy ramp, the storage ramp. During this storage ramp, this year they're going to put in crossing angles at Phoenix. So the beams actually cross at an angle and it'll restrict the collision vertex, which they'd like to do, localize it a bit better. Then there'll be RF rebucketing from 9 megahertz to the 28 megahertz. The 28 megahertz is what gives you the 360 RF buckets around the RHIC ring. They fill every third one, and that gives us our 120 bunches, and then actually they only fill 111 because of the board gaps. They'll remove the beam separation bumps so the beams can collide. They'll collimate the backgrounds away from the beam. They'll do a p-carbon polarization measurements of both beams so you know what polarization made it up the ramp, what you're starting with, and then they'll flip physics on and the run starts. So this was my interpretation of how to answer the question I was asked, how does RHIC prepare the beam for our experiment? Thank you for your attention.
Okay, thanks, Bill. Questions from the room for Bill? Yoshi, go ahead. And maybe, sorry, one quick thing. Could everyone please say your name before you ask the question? Go ahead.
Thanks for the nice talk. So my name is Yoshi. My question is sort of conceptual. So why is it the case that as you increase the energy of the beam, the polarization decreases?
Well, in RHIC with the Siberian snakes, ideally it doesn't. If you're in the AGS with a partial snake, you're hitting different depolarizing resonances depending on where the energy is versus this G gamma factor.
I mean,
And it's just that you're hitting a depolarizing resonance that's in tune with the precession. This is probably the best one. So if you don't have full snakes, and they don't have that in the AGS, as the beam is in there, it's rotating around this. As long as it's not in phase, whatever this perturbing force isn't in phase with the rotational frequency, it's not so bad. It'll be kicking it all different directions, some going in, some going bad. When that G gamma hits an integer, it means that there's a constant relation. They're in phase. So maybe it goes around 10 times, and then it comes back to the same spot where the perturbing force is, and it gets kicked, and it's going to try to depolarize it.
I was mostly talking about slide 26, where you list the polarization elements.
Oh, why do we lose polarization at all?
No, like how this polarization decreases as you go from LINAC to AGS and then to RHIC.
Everything has to be perfect to maintain polarization, and life isn't perfect. I think it's probably not a very satisfying answer, but it's all these various slight imperfections that you can't completely correct for. They try to do things adjusting the tunes to minimize these imperfection resonances that affect the polarization, but it's a complex system. They're large systems. You've got magnets that aren't perfect. You've got the placement of the magnets that aren't perfect. You try to account for it, and to me, it's a miracle that they can get the beam up to RHIC and it's polarized once. But I think the right answer is that life isn't perfect. In a perfect world where everything was perfect, I think theoretically you could maintain the whole 80% polarization all the way to the top.
I see. Thank you.
Fernando, go ahead.
Hi, thanks for the great talk. My name is Fernando. I'm actually just curious about the processes to basically strip all the electrons of either the hydrogen atom or these gold atoms. Because in my own understanding, this is a mechanical process, right?
Yeah. Well, it's not mechanical. It's electromagnetic, I think, more. They'll just have a thin foil in a transfer line, and a nucleus comes in. It's got a certain number of electrons going through it. It passes through that foil, and it'll strip off some of those electrons.
And it's not just a single layer of this foil, right? It's
Typically, it's just a single layer of the foil.
Okay.
The sources themselves will make nuclei that come in various charged states. But it's not until you get to the higher energies that they strip off all the electrons. And indeed, the last two inner shell electrons, as was pointed out here, don't get stripped off of gold until you go into RHIC.
Yeah, you go ahead.
I have two questions. Thanks. My name is Yu Hu. The first question is, can we get different luminosity in different collision point, like star as Phoenix, and how to do that?
You can do that. The crossing angle is one way you'll do it. It's much more problematic in polarized running than in heavy ions. In heavy ions, the beams have a finite size. I think the full width is on the order of a 0.5 millimeter or so, and in their Gaussian profile. So you can just steer the beams off center a little bit, so they miss a little bit. And when we ran I can't remember what we call that program. We're looking for the chiromagnetic effect with the beams that we held them at a constant rate through the store, 20 kilohertz. And they did this by off-steering them more early in the fill, and then as the beam decayed, they'd bring it more into collision. And if you recall, we ran star at an absolutely steady rate, and that was to minimize any rate-dependent systematics. In polarized protons, the fact that you've got a polarization profile, if you missteer those beams, you can have a very tough time trying to get a good estimate for what the polarization is of what you're colliding, because you're going to be on the tail of the two beams. The polarization is less. You don't know exactly where it is. If they're colliding head on, you know what the profile of the beam is, the physical profile. You know what the polarization profile is, and as the equation showed, you can correct for this. to figure out what the spin-dependent processes you're measuring. But so any missteering is typically not done in polarized protons.
I see.
By putting in a crossing angle like Phoenix will do, they'll get a lower luminosity than star will. Star will be colliding head on.
I see. I see. Okay. My second question is for the hijack, the calibration, right? So how often we need to do it?
It's running all the time. Unless it has to go down for maintenance. The gas jet is running all the time. They inject the beam. I think the data acquisition, they probably start only when they get to the top energy, and Elke could answer that question. But it's running all the time. Every fill, you're taking data with that. Okay. And the more data you get, the better your precision. At some point, you're going to limit out. But it's running essentially all the time.
I see. Okay, thank you.
Let's pause to take a quick question from the Zoom. Alexei, go ahead.
Yes, hi. So I suppose you can hear me.
Yes.
Yeah, perfect. So I have something related to the first question. So in the plans of EIC, if I recall correctly, the plan is to have the polarization on the level of 70% to ions and something like 70 or even 80% for electrons. So can you comment how you plan to achieve this and what would be the trickiest parts to do this?
I can't answer that question, but I can defer it to Elke here, who can answer or could give you some insight into that.
So for EIC, we do a lot of different things. First of all, we improve the polarization at the source and we improve the polarization at the HES. We still will have losses, and the HES is improved by putting in particular magnets which compensate for the depolarization. Then we transfer to RHIC and we install more snakes. Now we have 2 snakes per ring. For EIC, we will have 4 snakes per ring to compensate better for the depolarizing resonances which we have in RHIC. So that will kind of help us to increase the polarization for the hadron beam. The electron beam doesn't have depolarizing resonances. There we have a different effect, which is synchrotron radiation. It's a circle of turnoff effect, which acts differently whether your bunch is polarized up or down. In one case, it increases the polarization. In the other case, it depolarizes. And there we will replace all bunches every 2 minutes to keep the polarization high at 70%. So we have a kicker which does kick out and kick in, the same bunch. And that is how we kind of keep the polarization high in EIC in the electron beams. That is something, a completely new concept, so very exciting to get this to work.
And then clean living and careful tuning.
Yeah.
Okay, hopefully that answered your question, Alexei. Let's go back to the room. Go ahead.
I'm Gregory. Hi, Bill. Very impressive talk. One question, because for isobars, as you mentioned, there was an attempt to keep the rates, so basically luminosity, as stable as possible. What prevents us to keep running the same beam for more than, let's say, 8 hours, as you said? At 8 hours, we have to dump the beam. What prevents us to keep running?
Yeah, well, you've got beam losses. The vacuum pipe of the collider is a very good vacuum, and in particular, the superconducting parts, it's cryopumped, if you will. It's so cold if there's anything in there, it'll stick to the wall, any gas molecules. But it's not perfect, so you lose a small amount there. With the ion beams themselves will blow themselves up because of the Coulomb repulsion. When we're running ion beams with the stochastic cooling on in both planes, it can counteract that pretty effectively. But then just the collision of the beams, one against the other, takes a little bit of the beam away. When the beams cross one another, you can have an effect where even though they don't hit, you'll get a giant dipole resonance in the gold nucleus. It'll pop off a neutron. It's got the wrong rigidity. Won't make it around the ring many times. So various small things that just drop the intensity. But when they're running really cleanly, it's the burn off of the beam through the beam-beam interactions, whether they collide or not. And if they're not running so cleanly, it's, the vacuum pressure in the rings and such.
Thank you. We have time for maybe one more. Go ahead.
Hello, my name is Yichen Feng. I have a naive question about AGS energy, because we know the AGS energy can accelerate nucleons up to like 10 GeV, as you said, and the star fixed target energy is also kind of below 10 GeV. So my naive question is it possible to directly use the AGS beam to do the fixed target experiment, for example, in star?
Well, in STAR,
Yeah,
there was an experimental floor associated with the AGS, and I mentioned in the period after the booster was built in the 90s, when we were building the RHIC experiments, a lot of people in the field didn't have much experience in heavy ions. I'd been working 10 years before that at the Bevelak out in Berkeley. But so there were a lot of groups that got involved in fixed target experiments on the floor of the AGS. The beams out of the AGS are directly used in RHIC when we're running the lower energy fixed target. They'll set the magnets in RHIC to whatever that energy is, call it 5 or 7 GeV for a single beam. They'll inject it at 7 GeV and the beam just coasts around. They don't do anything to it. And that's why you may recall when we run that program, we would just leave the detectors on. They would dump the beam, inject the next one. Some of the stores would only last 10 minutes, 15 minutes, and then they would just decay away. So in that sense, we are directly using the AGS beam, and that RHIC isn't doing anything to it other than steering it around in a circle.
Yeah. So in future, maybe under the EIC construction, the kernel is not useful, or not useful for star, for example. Is it possible to move the star detector directly to the AGS location and connect them to
No. It weighs 1,200 tons. The star detector will get taken apart, and there's a plan to do that that'll take on the order of a year plus. I think the cradle is going to be reused by the EPIC detector, and Elke is the expert on that. There may be some other minor parts. I think the platforms are going to be used for the EPIC detector, but most of it will get scrapped.
Okay, thank you.
Okay, with that, we should move on. So let's thank Bill one more time.